So in this video, we're going to be looking at first ionization energy, successive ionization energies, and of course any trends in ionization energies across the period and down the group as well. Now starting off, we need to know what's meant by first ionization energy, and we say in the exam that is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions itself. Now you can see over here that I've got an atom over here, and it's going to be of course sodium in this case, and what we're trying to do is we're trying to remove the outermost electron, the highest energy electron, from each atom, each gaseous atom, to form of course a gaseous 1+ ion itself, right? But of course, because we're dealing with the first ionization energy, it has to be per mole, so we're going to be removing 1 mole of electrons here from 1 mole of these atoms to of course have 1 mole of gaseous 1+ ions being formed itself as well. Now if we were to look at this, right, we can actually give this a value, which in this case is going to be positive 496 kilojoules per mole. Basically, it's going to absorb 496 kilojoules per mole of actual atoms that we actually ionize itself. Now, if you were to write an equation for this, where of course I've got the example of sodium, it doesn't matter what element you're dealing with, it's always going to be the same. I would have of course 1 mole of gaseous sodium atoms, and that's going to form 1 mole of gaseous sodium ions itself, and then of course 1 mole of electrons, yeah, and that's concise, and of course it's going to fit our definition as well. Now the symbol that we actually give for the first ionization energy is very important, because it's just going to be delta H, and then of course we put IE1, IE meaning ionization energy, and then 1 meaning of course the first ionization energy. We'll come across this later on when we deal with enthalpy changes in module 3, but for now we'll just go with delta H as being similar to energy change in terms of what you've done at GCSE. Now in terms of this, you can see that the value of this is going to be plus 496, so we know of course this is going to be an endothermic process. If you were to have a positive value in any case, remember of course for energy change it's going to be endothermic. If it's going to be negative, of course we know it's going to be exothermic itself. So in this case we know that we're going to absorb 496 kilojoules per mole of actual atoms that we actually do the first ionization energy for, but we need to think about why it's going to be an endothermic value and actually explain that. Well, if we were to look at this, right, we know we've got a nucleus for sodium that has a charge of +11, and that's going to be attracting the outermost electron, which is going to be of course negatively charged. This attraction is going to be electrostatic, and what we need to say is that we're actually breaking a bond here. From GCSE, you need to remember that breaking a bond is an endothermic process. So energy is required to overcome the electrostatic attraction. This attraction over here is electrostatic because it involves a positive charge attracting a negative charge. And of course, it's going to be between the positive nucleus and the negative electron itself as well. Now, normally we say the lower the ionization energy is going to be, the easier it is to form an ion. Think about, of course, the ability to actually be oxidized itself. So substances, if they have a lower first ionization energy, they will be oxidized a lot easier as well. Yeah. So moving on, right, we need to look at the 3 factors that affect, of course, our ionization energy, and our ionization energy is going to be dependent upon the nuclear attraction itself. Now the nuclear attraction is basically just the attraction between our positive nucleus and our outermost electron in the case of first ionization energy, but generally nuclear attraction is going to be something that every electron experiences, right? Basically, it's just the attraction, the electrostatic attraction between the positive nucleus and the negative electrons themselves. Now, the first factor that affects our ionization energy is going to be nuclear charge. I've got here 2 atoms. I've got sodium, and then I've also got magnesium as well. And we can see, of course, we've got the following GCSE electron configuration. Sodium, in terms of its nuclear charge, because it's got 11 protons, it's going to have a +11 charge. Magnesium, because it's got 12 protons, it's going to have a +12 charge. Now if you were to think about this, right, the more protons we have, the greater the nuclear charge is going to be, the greater the attraction for these outer electrons is also going to be. So we know, of course, if it's harder to remove an electron, the first ionization energy, that energy required to move the outer electron, is going to be of course a lot greater as well. So we end up with a more endothermic value. Moving on to our next factor, atomic radius. If I were to look at, of course, atomic radius, I'm talking about the size of the atomic radius. And the further our electrons are going to be away, right, the, of course, weaker the nuclear attraction is going to be. So I've got here two examples of atoms over here with, of course, different atomic radiuses. In the case on the left, I've got, of course, helium. In the case on the right, I've got neon itself. Now, when I compare the two over here, I can see that the outermost electron, which is this one and this one, is going to be, of course, further away in neon. And if that electron is going to be further away, it's going to feel less of that nuclear attraction, of that positive nuclear charge. There's going to be a weaker attraction, and so our electron is going to be more easily removed. And what that means is that ionization energy is actually going to be lower itself as well. So yeah, moving on to our next one then, if you were to look at shielding, which in some cases is going to be called, of course, screening, right? We know, of course, we've got two atoms over here again. They're both going to be noble gases. I've got helium, and then I've also got over here neon as well. Now, if you were to look at this, right, we can see already neon is going to have, of course, an electron that's going to be further away compared to, of course, helium, and that's going to be, again, weaker in terms of the nuclear attraction, and so it's going to be more easily removed. But we've got to think about it in terms of the number of shells as well. Now, if you look at these electrons over here in this shell itself, right, what will actually happen is these electrons, more specifically this electron over here, is going to block the attraction that's coming from, of course, the positive nucleus to the outermost electron itself. Now, this effect is what we call shielding or screening, and essentially, basically what's happening is this electron over here is shielding the attraction of our positive nucleus to, of course, our outermost electron. That means that this outermost electron over here is not feeling as much attraction as it should. The attraction to the nucleus is going to be weaker. You've got less nuclear attraction, and so we know, of course, we end up with a lower first ionization energy itself, right? So that's shielding. Normally, the more shells you have, the more shielding you have, and so, of course, the weaker the nuclear attraction is, and the lower the first ionization energy is going to be. So yeah, there's our three factors done. If we were to look at how we would explain this in the exam, though, what I would normally do is, of course, remember NANCARs, where we're, of course, looking at nuclear attraction. That's a keyword we need to mention, nuclear charge, atomic radius, and of course shielding. If you mention all of these four every single time, you will always get full marks in every single one of these questions. And this method of using NANCARs, it can also be used to explain trends in ionization energy, electron affinity, and redox reactivity as well, so the ability to become oxidized or reduced itself. Now, just be aware that, of course, you can't actually use it for boiling and melting points because it has nothing to do with intermolecular forces. It only has to do with, of course, reactivity in terms of gaining and losing electrons, right? So yeah, moving on, right, in terms of our first trend, because there's a couple that we need to know, we know that ionization energy decreases down the group, right? Why is that the case? Well, you can see here, I've got two examples of atoms. I've got, of course, one atom over here, which is actually going to be helium again, and then I've got another one over here, which is going to be, of course, neon. If we were to look at these two over here, in terms of NANCARs, right, this is how we need to think about it. In terms of NANCARs, right, if we were to start off in terms of shielding, we know, of course, neon is going to have a greater number of shells. So going down the group, the number of shells is going to increase. We know, of course, this is group A that I'm drawing out over here, but of course we've got group 2 here as well. Same trend. If we were to look at it going down the group, any group whatsoever, the number of shells is going to increase, so shielding increases. That's our first point done. In terms of atomic radius, you can see the number of shells is increasing, so the atomic radius is also going to be increasing itself. Yeah, so there's our second point done. If we were to look at, let's say, NC, which is our next one, nuclear charge, going down the group, our nuclear charge is going to increase. We can see we've got +2 here, and then of course over here we've got plus, and then it's going to be 10 itself. Nuclear charge is going to, of course, increase our nuclear attraction. But the thing is, right, if I were to look at the number of shells increasing and the atomic radius increasing, these two factors, they decrease our, of course, nuclear attraction. Now, if I were to weigh them up, right, the effect of the atomic radius and shielding effects increasing, they will both outweigh our nuclear charge. And so, although that is the case, we still need to mention it in the exam, right? So we know, of course, nuclear charge increases down the group, but it's outweighed outweighed by the increase in atomic radius and shielding. What about, of course, our nuclear attraction? Because that's what we're trying to explain. Well, nuclear attraction, the attraction for the outer electron is going to decrease, and so we know our electron is going to be more easily lost. So it's easier to lose the outer electron in neon compared to something like helium. And of course, you can see the same trend follows with, of course, our group 2 metals going down the group itself. The first ionization energy is going to decrease, so they can lose the electrons more easily. So yeah, there's our last point done. Yeah, so moving on to our next trend then, if we were to look at, of course, ionization energy going across the period this time, we can see I've got two examples over here. Sometimes drawing out part of the electron configuration does help, especially the one from GCSE. If I've got sodium over here and then I've got magnesium over here, and I were to compare these two in terms of non-cars, we know first of all, in terms of non-cars, I'm going to start off with nuclear charge in this case because that's the most obvious one. Nuclear charge itself, that is going to increase. Right, so nuclear charge is going to increase. How do I know that? Well, I look at the atomic number of sodium, it's going to be 11, so our nuclear charge is plus 11. Magnesium is going to be 12, so it's going to be plus 12 itself. We know, of course, we've got more protons, the number of protons increases, so nuclear charge increases itself. So you're looking at our next factor then, you can see, of course, we're dealing with shielding next, right? So I'm going to skip over to S over here. In terms of shielding, right, we can see, of course, these two, they have the same number of shells. That means that their shielding is going to be similar, although magnesium, right, we've got an extra electron in there, so that might actually contribute to some shielding effect. That's why we normally say not the same, but we say similar instead. So yeah, shielding is going to be similar in both of them, so we don't need to worry about that. So what about the next one then? Well, we're dealing with atomic radius over here, and we need to think, of course, if I were to compare these two, we've already said that magnesium got a greater nuclear charge, but then if I were to look at them, they've both got the same number of shells, they've got similar shielding. If I were to think about the attraction, right, of all of these electrons to the positive nucleus, it's going to be stronger in the case of course, magnesium, because you've got, of course, a greater nuclear charge, and it's attracting these electrons from the same shell more strongly, because, of course, you've got plus 12 charge instead of a plus 11, and, of course, you're attracting the electrons in the third shell itself, but this time it's going to be more strongly, right? So in the case of atomic radius, they're going to be drawn in more, these electrons are going to be drawn in more, so our atomic radius is going to decrease itself. Looking at, of course, the next one, which is nuclear attraction, because that's atomic radius done. What does that mean in terms of nuclear attraction? Well, nuclear attraction itself as a whole, it's going to increase, so it's going to be harder to remove this outer electron itself in magnesium. Well, what does that mean in terms of first ionization energy? Well, generally, we're going to end up with first ionization energy increasing across the period. But the thing is, there's two exceptions that we need to be aware of. One of them is a dip between, of course, group 2 and group 3 over here, and another one between group 5 and group 6 over here itself as well. So going from magnesium to aluminium and then phosphorus to sulfur, right? So yeah, if you were to look at this, our exceptions between group 2 and 3, first of all, if you were to look at the electron configuration, where I have, of course, on the top over here, I've got magnesium, and then at the bottom over here, I've got aluminium. I'm just going to look at the third shell in both of these cases because I can't be bothered drawing the rest of them out. So if I were to look at this, right, magnesium is going to have, of course, 2 electrons in its outer shell, but if I were to look at aluminium, I've got 1, 2, and then I've got 3 over here in the p subshell. Now if I were to look at this, magnesium has its outermost electron in the s subshell, in the 3s subshell, whereas aluminium has the outermost electron in the 3p subshell. And what we can say is that this 3p subshell has got a higher energy than the 3s subshell, which it does. That means there's a slight increase in shielding, and this outweighs our increase in nuclear charge itself, and that's why we end up with, of course, a short dip. So if we were to look at our p subshell, it's going to be slightly more shielded, and of course that's going to cause our ionization energy to decrease, and that decrease is going to overpower the increase that we talked about of nuclear charge increasing, right? So yeah, in that case, looking at the next one, we're about between groups 5 and group 6, we end up with a decrease as well. If I were to look at it, right, I've got phosphorus at the top, I've got sulfur at the bottom over here, and again we're going to just draw the third shell out. If we were to look at the electron configuration, right, in terms of phosphorus, it's going to be 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and the sixth electron is here. Now if I were to look at, of course, the outermost electron, we're going to go with this one over here for phosphorus and this one over here for sulfur itself. If I look at the shielding between phosphorus and sulfur, the atoms themselves, they're going to have similar shielding, and of course we're removing the electron from the 3p subshell. But the thing is, when we look at sulfur, because we've got a pair of electrons in one orbital, they're going to repel each other, because when you take two negative things and you put them next to each other, they're going to repel each other. We end up with electron pair repulsion, and so it's going to be easier to remove the electron. And remember, if it's easier to remove an electron, the first ionization energy is going to be lower. It requires less energy to overcome the attraction between that positive nucleus and of course our negative electron itself. So yeah, moving on then, if we were to look at successive ionization energies, of course we know we can remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions, but you can actually end up removing, right, the second lot, one after that, and then of course a third lot of moles to form of course 3 moles of gaseous 3+ ions and so on. The general name we actually call it is going to be of course successive ionization energies. Now in terms of the second ionization energy as an example, in this case, right, we're looking at the energy needed to remove again 1 electron from each ion in 1 mole of gaseous 1+ ions. So in other words, 1 mole of electrons from 1 mole of gaseous 1+ ions, and we're trying to form 1 mole of gaseous 2+ ions in this case, right? And we can actually show the different types of ionization energies we've got with different symbols. We can end up with delta H IE1, IE2, IE3, and that's going to be for the first, that's going to be for the second, and that's going to be for the third ionization energy itself as well. Now the number of successive ionization energies we have, a trend that you need to remember is that it's going to be the same as the charge of the ion formed. So how I like to actually draw out my ionization energies is to say, okay, if I'm looking at the first ionization energy, I'm forming 1 mole of gaseous 1+ sodium ions. If I'm looking at the second, I'm forming 1 mole of gaseous 2+ sodium ions, and again it's going to be a gas. And then if I'm looking at third, it's going to be 1 mole of gaseous 3+ ions itself as well. Don't forget the electrons there. I like to start with the products because it stops me from making silly unwanted mistakes. So yeah, what must I have started with in this case? Well, of course, sodium plus ion must have come from sodium that is a gas, and then of course sodium 2+ ions must have come from sodium 1+ ions, which is a gas again, and then of course sodium 3+ ions must have come from sodium 2+ ions, which is a gas again. You can see here I've got first, second and third ionization energies, and that's how we write the equations for that itself, right? So moving on, if we were to look at our next trend, which is going to be the trend in successive ionization energies, very important. This actually helps us discover stuff about our electrons and their structure itself. Now if we look at ionization energies in terms of their trend, we know that ionization energy increases as more electrons are going to be removed, right? Why is that the case? Well, if I were to take, let's say, a sodium ion, and of course that sodium ion were to have of course 11 electrons itself, and that's what it's attracting, the 11 plus charge, so the 11 protons are going to be attracting 11 electrons. If I remove an electron, I will be left with 11 protons this time attracting 10 electrons. But because we've got the same nuclear charge attracting fewer electrons, they're going to attract of course more strongly compared to before. And the more of course electrons we remove, right, the stronger the actual nuclear attraction will be for those electrons. So yeah, how do we wear this in the exam? Well, we just say we've got the same number of protons and the same nuclear charge attracting fewer electrons more strongly. We're basically removing these electrons from a more positive ion itself, yeah, and that's what we need to say, all of this, to get the marks itself. So yeah, if we were to look at successive ionization energies, why is this important? How do we use it in the theory of our actual atoms and atomic structure itself. Well, if we were to look at it, right, let's see if I've got in this example over here, I've got an element, and of course I've got some first ionization energy, second, third, fourth ionization energy data, and so on, all the way up to 8 basically. What I'm seeing is here is I've got, yes, a general increase in terms of first ionization energy where it's gradually going up. But the thing is, if I look at removing the 6th electron compared to 5, 4, 3, 2, 1, I will actually end up with a massive jump itself, right? And that massive jump is down to us, of course, breaking into a new shell. Now, if you look at this, right, you can see, of course, I've got here another atom. We can figure out what it is as well. I've got over here, of course, a bunch of different electrons, and I'm going to remove the first electron. There's first ionization energy. There's the second ionization energy. There's the third ionization energy. There's the fourth one. There's the fifth one. But what you'll notice is, in this case, is that we're actually removing an electron now from a shell closer to the nucleus. So the next one, we'll just go with any random one. It's going to be this one over here. That's what's going to create a massive jump, right? So this one over here is going to be, of course, our electron that's from a shell closer to the nucleus. Now, what does that mean? Well, if I've got 5 electrons here and I've got a big jump after that, that means in our outermost shell, we've got 5 electrons. That means that this compound must belong to, of course, group 5, because group 5 elements will have 5 electrons in their outer shell. And with a bit more information, you can actually figure out what it is. Of course, you know it's in group 5, but if the examiner told you it's in period 2 or period 3, you could figure it out easily from that itself. So yeah, looking at a common exam question then, it could actually ask you to explain, you know, how you know this element's in group 5, or it could ask you to explain how do you know it's got 5 electrons in its outer shell. Well, you would say, of course, there's large increases, and these large increases are caused when a new shell is broken into, and of course the electron is going to be removed from a shell closer to the nucleus itself. Just be specific about what kind of jump you get. So between 5 and 6, talk about the 6th electron being removed is from a shell closer to the nucleus, and so on. So yeah, I've got a task for you to do. Feel free to pause the video and have a go at the following. Resume once you're ready to move on. So yeah, in that case, if I were to look at the first one, we're asked to write the first ionization energy for chlorine. Common exam question. All I'm going to do is take 1 mole of gaseous 1+ ions, because of course it's the first ionization energy. I'm forming 1+ ions. I know it looks a bit weird, but it's still going to be correct. Remember the state symbols as well. I'm going to end up forming electrons, and then of course, what's that come from? Well, of course, look at the charge, and I'm just going to make a difference of 1. So I've got chlorine, and then it's going to be a gas itself. Remember, it's going to be Cl on its own because it's gaseous atoms. We're not looking at molecules, giant covalent, ionic and whatnot lattices. We're just looking at 1 mole of gaseous atoms. Look back at the definition. Look at the next one. Write the equation for the third ionization energy of barium 3+. So we know, of course, we must end up with a charge of 3+. So we start off with our product, barium, don't forget it's a gas, and we end up with a 3+ charge and an electron in this case, and that comes from barium. We've got to think now, take 1 off the charge, you end up with 2+, which is of course a gas as well. Don't forget the states as well. So yeah, look at the next one. Looking at C, we're asked to write the equation for the 9th ionization energy for potassium. Doesn't matter what you're looking at, in this case it's 9+, so we know we've got K. Looks a bit weird again. 9+, that's a gas, and we're forming an electron, and that's going to be from, of course, K, and then it's going to be 8+, which of course is going to be a gas as well. Always do the equations backwards, it stops the silly mistake. Looking at the next question over here, we're told the 1st to 8th successive ionization energies in kilojoules per mole of an element in period 3 are shown here, and of course we can see we've got some data. We're asked to state the formula of the actual element itself as well. Now think back to successive ionization energies. You've got, of course, kind of regular data over here, but if you were to look at it in terms of trends, right, you can see of course it's increasing, as it should do, because you've got the same number of protons attracting fewer electrons. You've got, of course, a more positive ion in this case attracting the electrons more strongly. If you were to look at it though, right, between of course this value and this value, you actually end up with a massive jump, because these 3 values over here, they seem to fit one trend, but then these 5 electrons that you're removing one after another, they're going to have of course their own trend where it's going to be very similar in terms of the data. Now the big jump is from 5th to 6th, so we know after the 5th electron, when we're removing the 6th electron, That sixth electron is from a shell close to the nucleus. So from the question, we know it's going to be in period 3. We know it's going to be in, of course, group 5. And so we know, looking at our periodic table, our answer is going to be phosphorus itself. So yeah, moving on to the next task then. Feel free to pause the video and have a go at the following task and resume once you're ready to go over the answers. So yeah, we're told over here that the first 5 successive ionization energies of element Y are shown below. Of course, we're asked for the formula of chloride Y. That's kind of how these questions follow. If we were to look at the data, we can see, of course, the big jump is going to be between the first and the second over here. It is generally increasing, but the big jump is going to be between the first and the second. Now, what does that mean? Well, it means that, of course, we've got in our outermost shell 1 electron itself, right? So that means, of course, our element, our atom that we're assuming is going to, of course, belong to group 1. Group 1 atoms, they're going to form group 1 charges, and that's going to be 1 plus itself. So we end up with Y being positive. Cl is going to be minus. So our formula, if we just drop and swap, not that we need to, is YCO. There's that one done. So you're looking at the next one, which sequence has elements in order of increasing first ionization energy. This one's a bit trickier, but it comes up once every 2 years. Multiple choice question. Well, if you look at it right, you've got, of course, sodium, magnesium, aluminium. In terms of our trend going across the period, right, we know, of course, our ionization energy is going to, of course, increase. Going down the group itself, we know ionization energy is going to decrease. But just remember, going across the period between groups 2 to 3, and then of course 5 to 6, it actually decreases itself. So we look at this one, we've got sodium, magnesium, aluminium. Sodium to magnesium, it increases, and then of course aluminium, that's going to decrease itself. So that's not, of course, going to be the right answer. Look at the next one. Magnesium to aluminium is, of course, going to decrease. We know, of course, that's going to be incorrect as well, because, of course, aluminium is going to have a lower first ionization energy compared to magnesium. Look at the next one. You've got aluminium, silicon, and then phosphorus. If you were to look at aluminium, yes, it does have a lower first ionization energy compared to silicon, because silicon is in group 4. And then phosphorus, right, because we've got group 4 to 5, we know, of course, phosphorus is going to, of course, have a greater nuclear charge. It doesn't have anything weird with it. Of course, the ionization energy is going to increase itself. So that's actually going to be the answer. Look at the last one. Why is the last one going to be wrong? Well, silicon's in group 4, 5, and then 6. Between 5 and 6, phosphorus and sulfur, we know, of course, we end up with a decrease in the ionization energy itself. So yeah, our answer is going to be C in this case.